Well, thank you very much. So I'm going to, this is going to be slightly funny talk, but I hope sort of by the end that I'll have given you some flavor of where I've got to in the study of these phenomena called drumlins. So that's not a drumlin. And if I was giving prizes, I'd probably give one if you can tell me where that is, but not now, maybe later. But I thought, because when I was flying over here, I thought, well, I mean, nobody's ever going to have heard of me. And so I thought I should maybe explain a little bit, just as preamble as to some of the problems I'm working on now. So as KK says, geoscience is mostly what I do. It's not all of what I do. But I'd say largely interested these days. I'm interested in problems as they occur to me. And here are some. So cave scallops are these. I don't know if you can. I'm going to use. You can see it. Yeah, but I have this fantastic thing here, which is at least I can see this, and I can beat some members of the audience if necessary. So these things up here are scallops in an ice cave in this case, and they also form in limestone caves. And then there's a question as to why they and how they form. This is a sea stack, which is about 2 kilometers from where I live in the west of Ireland, and it forms from the cliff as it erodes, and you form these isolated islands. This one's about 100 meters offshore, and the question is, how does that happen? I'm interested in dendrites in solidifying alloys and the problem of how you describe their microstructure. I'm interested in, have been for a long time, frost heave, which forms these hummocks. These are in Lapland in northern Finland, and it forms through a process called differential frost heave. So those are some of the things that I'm presently and have been interested in for quite some time. But I'm going to talk about drumlins. So the first thing I better do is to tell you what a drumlin is, although, as I will say later, you ought to know. So these are drumlins in the Ards Peninsula in Northern Ireland. So they're these small hills, elevation, typically in the order of 10 meters. It varies a bit. I'm standing on the top of one here, taking a photograph, looking, I think, inland. And I put this up now. You normally see this at the end of the talk. I put it up now just to kind of apologize for the fact that when I started doing this, which was in 2000, the first published paper, and I thought, as you generally do, well, okay, so we're going to form these things. There'll be a model. We'll solve it. It'll be done. Move on to the next thing. And here I am, 25 years later, still worrying about this. Here's a drumlin in Wisconsin. This is also in Wisconsin, and you recognize the drumlinized topography because of the rolling of the road as it goes up and down. This is a drumlin in County Clare in west of Ireland, and I'm again standing on top of a drumlin. This is in Glasgow. You recognize Glasgow is covered in drumlins. You recognize that's a drumlin because the road is straight, and then all of a sudden it goes up over the hill at the end. So the way this would work is that the drumlin, the elevation of it is going from left to right there. These are drumlinized topography in Cape Cod, near Woods Hole, in fact. And I'm going to spend a little time telling you about the origin of the word, because when you study something like this for this amount of time, you get interested in all kinds of weird aspects of it. And the weird aspect here is, where does the word drumlin come from? So, as you can see, I can't see that. So you can see at the top the word drumlin. This comes from the Oxford English Dictionary. And if you look down, so it says up at the top, drumlin is a diminutive of drum, and that's true. It's a little bit like duckling, diminutive of duck. Lin is the Scottish version of that, so there's a word called goblin, which means an unfledged bird. So my feeling is that the drumlin comes from the Scottish diminutive of drum, and then the word drum down below comes from the Irish word drim, spelt variously, D-R-U-I-M. And then what they've done is that they've found some original citations of where these words originated. So there are three in here. I'm going to talk about Innes, Robert Innes. Can't see the red thing anywhere. Right, so it's there somewhere, is it? So Robert Innes, letter to Bishop Nicholson. And then there's the statistical account of Scotland. And then there's this paper by Bryce. Where has that gone? Down here somewhere. Here. I don't know, up there. And so the Robert Innes, this is he writes on several subjects of natural interest to the local, the late meaning, not that he's actually dead, but most recently, Archbishop of Cashel. And here's his diagram of what he called drims, which are these ridges. But here is what they actually look like on a digital elevation model. And these are not drumlins at all. These are fossilized dunes, it turns out. These are in McGilligan Strand on the shores of Lough Foyle in Northern Ireland. And then in Sinclair's Statistical Account of Scotland, which is a huge compendium of all kinds of knowledge about Scottish parishes, a lot of it drawn from accounts of the local priests, he talks about drums and actually refers back to an account by Tacitus of the Roman war of the Romans against the Caledonians. And he refers in here to sort of down, where's it gone? There it is. So he refers to colles, which means hills in Latin, and as if the hills were where the Roman soldiers took up their position on the hills and the Caledonians in the lower spaces. And here are the particular features he's referring to, but these are not drumlins either. These are meltwater channels. So they're associated with ice, but they're actually not under ice. And finally, we have Bryce's paper, and he talks about the origin of the word drum and drumlin, about 7 lines down, where he says the word drumlin coined by the peasantry. And that's the first instance of this word that I know of in the published literature. So that was in 1833, and these features have been of interest for in excess of 200 years. Interestingly, in this list, and it's a partial list, is that the papers by Hall and Bryce, they understand, Hall is talking about Scottish similar features called crag and tails, of which the best known example is the Royal Mile down from Edinburgh Castle. And but they're both talking about the transport of material, but they both, because it's so early, they both think the transport is by the biblical flood, because between about 1800 and 1850 was the transition in geology from an assumption that everything was done as the Bible said, and therefore everything was transported by floods, to the realization, really due largely to Agassiz, that large ice sheets had covered large parts of Europe, including Britain, and also, in fact, North America and elsewhere in the Northern Hemisphere. And so when you get to Kinahan and Close in the 1860s and 70s, by that stage it's recognized that these features, the drumlins, are formed under ice as it flows out. Ice, although it's a solid, on a long time scale, flows basically like a viscous fluid. And the story here is that, as it says down here at the bottom, you start out with floods, the biblical type of floods. You then build up through these theoretical discussions a pair of concepts of how do you grow drumlins, and the one idea is that they're depositional features. The sediment of which they're formed is laid down and then carved by the ice, or that they're and I said that slightly wrongly. Depositional meaning essentially constructional, so where a level floor of sediment will be molded by ice into corrugated features, including these hills. Or another idea is that you have a level floor of ice, and the ice then erodes it and forms the pattern as it does so. There have been other ideas, and the flood idea was revived by John Shaw, principally. I want to say a little bit about how my involvement in this has kind of come about over the time. It really starts with Chris Clark, who's up there on the left, and behind him, drumlins in Clew Bay and Westport in the west of Ireland, which march out into the sea so that they're dramatically visible. And Chris Clark, we got together, we had a grant, and we had a series of workshops in which we would discuss various ideas of how to get these things formed. And there's a picture of us sitting around at one of these workshops, a little bit later, actually. I mentioned earlier Glasgow. So if you stare up there, if you can see, I put a little red cross in there. This is Glasgow. This is a digital elevation map, which is basically giving a picture of the terrain. And all of these corrugations, these are all drumlins. The flat bit in the middle is the River Clyde going through the middle of Glasgow. And the red mark, which is, I don't know, what's an X or whatever it is actually a drumlin above the river, and that's where the University of Glasgow is. So the University of Glasgow is actually built on a drumlin. I think the University of Limerick is also actually built on a drumlin. And here are some drumlins in a digital elevation model, and this is in the Puget Lowlands, and the whole of this area is covered in drumlins. And I was pleased as I walked to the campus this morning to realize that the whole place is built on a drumlin. The principal feature about drumlins, and you get it well from this digital elevation model, which is, you can see up here in the top right, this is the red square marks the area. So it's towards the north of Ireland. And the drumlins here, the scale going from, well, there's a scale bar there, which is, I think, 10 kilometers. And so all these little small features, these are all drumlins. And they pockmark the landscape. So as you drive through these things, you see these rolling hills, which eventually you get to recognize. But if you look at this larger scale, you see that there's essentially a pattern. And that's the idea of what we're going to try and describe them as. There are different forms of drumlins. The original, there's a different type called rib moraine or Rogan moraine, which is indicated here. This is in Sweden, and the ribs, which are these features starting at the dark bits are water. So it's the flooding of the lake indicates the features. With this is just an aerial photograph. This will be in southern Sweden. If you can see, there's a sort of a ridge of material going across here, which is a rib moraine. Here is again in Ireland, where the ice flow is coming down from the top right. And the interesting thing here is that you have these long lineations, which are irregular. And when you go out and look at some of these things by the road, you just see a mild rise. They can be 2-3 meters high. So they're features that you see better in this kind of picture than you might actually do if you were on the on the surface. But the ice comes along, and then it hits an escarpment, and as it goes over the escarpment, the drumlins change shape. They become less lineated and become more sort of circular. And the extreme version of the lineations are these things which are called megascale glacial lineations. So these can be hundreds of kilometers long. This is northern Canada. I think it's the former Dubont ice stream, and it's, I think, to the left of Hudson Bay, to the west of Hudson Bay, I should say. And so these are very long features which were only recognized once satellite photographs came in. This is a false color satellite photograph. So I'm going to try and tell you the story a little bit about how we try and build a theory of it. And the basic idea is that it's instability. You produce spatial pattern. I suppose in this audience, everybody knows spatial pattern arises particularly in biological systems through instabilities. The same thing happens in many different systems in the Earth. You form dunes, as here, by an instability, there where it's wind acting or blowing over sand. In water, you form roll waves. So anytime it rains a lot, which maybe it does here, although I have no experience of that, and you go down you have a water flowing down a steep incline, the regular flow will break up into sort of periodic waves, which are these things, roll waves. So the idea of the instability theory is that we're going to produce pattern, we're going to produce undulations in the surface, and we hope that we're going to produce everything from rib moraine through drumlin. So rib moraine is sort of like transverse dunes. They're ridges, but orthogonal to the ice flow. Drumlins, which are sort of circular or elliptical kinds of shapes. And then as they become longer, lineations, and then eventually these megascale glacial lineations. And that's sort of the challenge. And there have been, in a big literature, there are lots of attempts to try and simulate these things. And this is one which I think is just not correct. This is another one which I think is probably not correct, but it's quite different from what I'm going to talk about. So the basis of the model, I'm going to slow this down in a minute to try and actually talk some mathematics, but and the basis of the model is that you have ice. So you have an ice sheet, which might be of depth, let's say 1,000 meters. The ice flows over a substrate, which could be bedrock, but more normally you think of as consisting of a material called subglacial till. And subglacial till you should just think of as sort of like soil. It's not soil, it's not organic, but it's a granular material. Subglacial till you recognize if you go out and look around. I haven't seen any here, but you recognize it because it has a sort of bimodal grain distribution. It's a lot of fine silt, clay kind of material together with larger clasts, cobbles, boulders, and the two are sort of mixed up. And the reason for that bimodality is that the larger rocks are ground up, they're fractured or plucked from bedrock, and then they progress to grind against each other in a process of comminution, which produces fine grains. So that material is thought to move, and it will move providing the ice at the base of the ice sheet gets up to the melting temperature. So, and that can happen and does happen. And the reason that happens, although ice is cold and maybe very cold at the surface, is that ice is really an insulator, and you have heat sources from the base. Geothermal heat is actually sufficient to raise the temperature to the melting temperature. And if it gets to the melting temperature, you will then start to produce water. So the three ingredients in this theory are going to be ice flowing as a viscous material, till underneath flowing and deforming in some way, and as well between the ice and the till, a water layer. The water will actually saturate the till. So the till will be a saturated granular medium. And the water has a sort of dual role. It saturates and then allows the till to deform, but also the concept is that it can form what you might think of as puddles at the interface between the ice and the till. So I've tried to kind of indicate this here, where you see a water layer there, which is quite thick, but then kind of pinches out. And in particular, there's another diagram, I think, here, which is also a cartoon where, slightly different cartoon from Neil Everson, where you have an ice layer on top. Actually, in his cartoon, the ice is full of dirt as well. There is water-saturated till below, and then an interfacial water film. But the important point about the interfacial water film is that it doesn't completely lubricate the ice, because you have large particles which stick up into the ice and provide a resistance. So here's my slide of equations. So I'm going to try and talk you through some of these things. And this, I should say, it says here up the latest theory, the latest version of this theory. This theory has evolved over the years. In its first versions, it didn't have any water flow in it. Now, or it had a sort of passive water flow. So I wanted to talk about this. The three basic ingredients are that you have you conserve everything. So you have a sediment conservation law, which is this thing. B is the elevation of the surface of the till. And the equation to describe it is called the Exner equation in geomorphology. And it's a normal conservation law where you have the rate of change of the elevation is due to several things which are fluxes. So you have an advective flux here, and then you have two diffusive-like terms. I'll talk about them in a minute. You also have down at the bottom, what looks like an evolution equation for the variable S. S is the base of the ice sheet. So if you can see this in this cartoon, I mean, it's a cartoon. S is the base of the yellow stuff, which is the ice. B is roughly speaking, the surface of the till, which is saturated. And then between S and B, there is a water film, which is kind of indicated here, but you have these particles of rock sticking up into it. So we have conservation of sediment. We have something that looks a bit like conservation of the ice surface, but actually this comes from describing ice flow. But what you do, well, I'll get to that in a minute. But this comes from ice flow. And then you have another equation which tells you what's happening in the water film. So this is just a lubrication theory for the hydraulic potential. And then you have a lot of algebraic stuff, which I will tell you a little bit about. Now, there's a few extra variables in there, which I need to describe. So you will see up at the top, the first term on the right has a gradient of n. So n is a very important concept in this theory, as in anything really to do with saturated granular media. It's the effective pressure. So it is the difference between the overburden ice pressure that's pressing down and the water pressure that's in the pore space. And the effective pressure will be positive, is positive in general. And when you have a gradient of it, the Terzagh's principle of soil mechanics says that the deformation of soil, water-saturated soil, is due to the effective stress, or in this case, the effective pressure. That's what makes the granular material move. So I hope you'll just sort of take that on trust. And then the consequence of that is that there is a squeezing term. So if you have a gradient of the effective pressure in the till, it will cause motion of the till, and I've modeled this here. You can sort of recognize that because of the A cubed, this is a lubrication type, theory type expression in which A, the capital A that up there, is the depth of the deformable till. So you think ice is behaving viscously, water is behaving like water, and the till we're thinking of here as being a bit like a viscous material, although the viscosity, if it's a viscosity, is more nearly like a plastic kind of flow. But we're thinking of the thickness of this layer as being some finite quantity, which I'm calling A. Now, the point, because it's a granular material, the thickness of the deformation is going to be controlled by the depth at which the yield stress is reached. And the yield stress for a granular material is the stress, it's equal to a coefficient of friction times the effective pressure. So if the effective pressure is a variable, which it is, then the depth as you go down to where the yield stress is reached will vary with that effective pressure because of the increase of the effective pressure with gravity as you go down into the till. So that's what that term, the first term on the right, describes, which is in the red thing, if I can find the red thing, which is, I can't even see it. It's there, and then it's there. And the second term on the right describes sediment transport by water flow. So we all know that in rivers, sediment is transported in two ways, either suspended load, suspended sediment, fine material, or as bed load. So when you go to the beach, if it's a rocky beach, you listen to the crash of the waves, that is bed load. It's the rocks going backwards and forwards as the tide goes in and out. And that is described in sediment transport theories by a term like this, where you have some effective stress tau E, and tau E is given in terms of the gradient of this hydraulic potential, basically. The hydraulic potential itself, then in the second equation, is this lubrication theory, and that's more or less self-evident. It's just what you would get from ordinary lubrication theory, except there's no time derivatives because they're very small. And then you have some algebraic bits, and I'm going to, let me jump down now to the bottom equation. So I said this was something to do with ice flow. What actually happens is that this is a kinematic condition for the ice flow. So the ice is viscous, the Reynolds number is 0, and we take it as a constant viscosity, so I have a biharmonic stream function. I assume that the slope of S, the slope of these drumlins, is small, which it is. Typical height, 10 meters, typical length, 600 meters, kilometer. And so what I can then do is I can take the biharmonic equation, boundary conditions at the interface, linearize the conditions at the interface about the flat surface, which means I can then solve the problem. It's a linear problem now, and I can solve it for the ice flow Fourier transform. And then what happens with that is that when you write down the kinematic boundary condition, it turns into this thing at the bottom. You have essentially the rate of change, material rate of change of the base of the ice surface is equal to some Fourier convolution of some kernel, which I call J, with something that is this quantity phi, which is something to do with the normal stress in the ice, and is given, is related actually to the hydraulic potential, which is up there. So now the two other things I want to say, there's a geometric relation between B and S and the thickness of the water film, which is just that. I have two other equations up here. The A, this is the thickness of the deforming till layer, and it's got two ingredients. Well, basically what it's saying is that the thickness is the difference between the basal shear stress exerted on the till divided by the coefficient of friction minus the effective pressure, because that gives you effectively the depth where you get to the yield stress. And the stress that's exerted on the till is given by something called the sliding law, which is a whole separate business, which I'm not going to go into, but involves the deformation of ice as it moves over a rough bed. And there's a relation when you do that there is a sliding velocity, which is non-zero. So it's a viscous fluid, viscous ice, but you don't have the no-slip condition. You have a relation between stress and velocity, which is the sliding law. And that sliding law depends on the effective pressure, because when the effective pressure goes to zero, that says the water pressure equals the ice overburden pressure. The ice is floating, there's no resistance. So the dependence of the relation between stress and velocity depends also on this effective pressure. The other equation, I'm nearly done with this, is that you need a relation between the thickness of the water film, H, and the effective pressure, N. And as I just said, if the effective pressure goes to zero, that means you're floating, starting to float the glacier, and so the water film is going to increase in thickness. So you have an inverse relation between H and N. We've defined it in this way. I should say this is entirely made up. You need such a relation. I would like to be able to tell you there is some physical description that produces that, and there is not. And that's one of many different ways in which this theory could be improved. This model is all written down dimensionlessly. This parameter delta in reality is going to be very small, 10 to the minus 3. Beta is going to be small, 10 to the minus 2, I think. Gamma is going to be small, 10 to the minus 3. So you see plenty of opportunity for doing nice asymptotic things. Can you do them? Can I do them? I don't think so, but there is certainly scope for at least asking the question, could you analyze this model? But as I've tried to make clear, this model has been, in my experience, about the worst model ever, because it's not something you write down and it's done. It just keeps evolving. But what I'm going to do is I'm going to show you two things. I'm going to show you what you can do easily, which is linear stability. And there's two different kinds of instabilities in here. So there's what I'm calling a ribbing instability. That is basically analogous to the formation of transverse dunes. So wind blows over sand. The top layer of the sand moves. It's kind of like the till moving. The wind is like the ice. And you form transverse dunes if the wind is going in one direction. So that's an instability associated with motion of the substrate, in this case, motion of the till. But there's another instability mechanism in this model, which is important, which is what I'm calling a rilling instability, and that is associated with the sediment transport due to water flow. So when water flows down a hill slope, which is erodible, that is unstable, and it will form small channels called rivulets, called rills, which over time will gradually evolve and form the river systems that you see in the landscape. So what this diagram is with a choice of sensible looking parameters, it's a diagram. The color scale is the growth rate. So zero growth rate is blue down at the bottom. Well, it eventually becomes negative. And then the red stuff is unstable. Actually, pretty much everything in here is unstable. And the K1 is the downstream wave number, and the K2 is up here somewhere. Well, it's at the other end of the pointer if I can find out where it's gone. The K2 is the cross-stream wave number. So I've called this ribbing instability because the maximum growth rate is down here. So it's essentially when K2 is 0. So these are transverse features. There's variation downstream, but not across stream. And that happens, the parameter that's being varied here is this lambda, which you have forgotten about, but it's in this water film, what I've called here a water film compression condition, sometimes called a closure condition. This is the thing I made up. So I'm varying a parameter, which I don't know what it is, and producing instability, which corresponds to the formation of ribs. But if you increase that parameter to 2, you get an instability in which the maximum growth rate has moved up and now has both wave numbers. So these are now two-dimensional patterns, if you like, associated naturally with drumlins. And then if you increase lambda to 10, you shift the maximum growth rate over to the left, and where the downstream wave number here is K1 is 1 or 2 or so, and the K2 is much larger. So you're shifting from transverse ribs, sort of two-dimensional drumlin type shapes, to longitudinal downslope lineations. And so that's what you can do with instability, and then you jump straight from there to trying to solve this thing numerically. So this is the kind of best version, and I won't go through the listing, but and the numerical method, this was really developed by James Fannin in his PhD thesis, along with Ian Moyles, who was a postdoc at the time. And they did a sort of mixture. It's natural because what you're going to do is you're going to solve this problem on a square domain, sort of in the middle of an ice sheet of size, let's say 5 by 5 kilometers. And so it's sort of natural to use periodic boundary conditions. And so that's what we did. And then the very first versions of this, I wrote a code in the kind of prehistory, which used a spectral method. And the reason you might want to use a spectral method, apart from the periodic boundary conditions, is because up here somewhere, I don't know where this, there it is. So this J star phi, this is a Fourier convolution, so it's sort of easy to use spectral methods to jump in and out of spectral space. But in fact, what they ended up doing was that they used partly spectral and partly finite difference, and things sort of work. But the other issue that you have is that you've got all these various parameters, beta, gamma, and delta, which are all small. And it turns out that the one that's difficult to deal with is the delta. And it's quite hard to get that small. So what I'm going to do is, well, I'll skip past this because this problem had a lot of kind of initial difficulties to surmount. One of the principal difficulties, was that you have ice flowing over undulating sediment. You're trying to grow the sediment into a waveform. The ice then separates and you get cavities. So now you've got to deal with, we're solving for the ice flow, but actually the ice is separating. So now that becomes a free boundary on the bed. How do you deal with that? Well, you can kind of deal with that in ways that I won't go into. And there are other issues to do with internal stratification and also the three-dimensionality of the forms, although the addition of the water flow helps this work. So here's an early, we're looking down now on a square grid. The units here are dimensionless. I should say then what the scales are. The length scale that we're talking about that comes out, you scale the problem. The length scale is 640 meters, which is a typical sort of length of a drumlin. Some are longer. And so you have kind of 10 of these. And this was an early computation by Mike Chapoigna of what the result of starting with this, which is a small amplitude noise basically, which you can't see, dimensionless amplitude. And then what happens is that you rapidly grow things of a certain wavelength, which look kind of rib-like. I think in this version there's not this. There's an earlier version of how water flow was described, and you get things. You get waves which are roughly speaking rib-like, in which you get high red bits, low blue bits, and they propagate downstream. And here's another one, which is sort of similar. And then there's a bit of a, you're going to ask a question.
That was the idea.
Okay.
I can wait until after.
No, you can ask now.
So do the length scales that you get as this evolves, do they correspond with the
Yes.
wave numbers that you got in?
Yes. And I mean, the good thing about this theory, so there are some, I probably sound like I'm kind of beating this theory a bit, but there are good things about this. The good things are that when you do all this scaling stuff, which you're just kind of doing the best you can, and you're doing it, you're not, when you do it, you do it with things like typical ice velocities and typical parameters, which are not bad. You get the right wavelengths coming out. So that's a kind of big signal that something is good about this.
But it also means that the process is dominated by the linear process.
No. Because almost as soon as these things grow, cavities form, and the whole thing is completely nonlinear.
But you get the length scales from the linear analysis.
The linear, well, and I mean, the other thing to say is, of course, you can change parameters and it'll shift around the place. So, but the stability gives you the right length scale in terms of, but it's of course orders of magnitude, I would say. So more movies. These are James Fannon's one, in which he's now on. He's now on a dimensional variable. So evidently the length scale is 2 pi, but it's I'm not thinking that, but it's so 6 kilometers by 6 kilometers, and the elevation. So this is the elevation of the bed surface, which is what you would see, and the high stuff goes up to 1.5 meters, and the low stuff goes down to minus 2.5. So you have an elevation of 4 meters. I think that's a bit low, but whoops, gone the wrong way. So let's see if this works. So we start with again almost small amplitude noise. You get similar kind of things, but this is now the kind of, if you like, latest version of the theory. And there's going to be a bunch of these. And up at the top, it tells you what the parameters are. And the parameters are the 3 principal ones, these beta, gamma, and delta. And you see delta in here is 0.1, and it should be 10 to the minus 3 or something like that. And it's because he can't run this at those very small delta values. And there's features of this, which I'll point out a bit later. This is the same, but now what these black lines are lines of constant hydraulic potential. So this is sort of telling you where the water is going. And when the black lines come together, it's concentrating the water flow. So you don't get an awful lot out of this, but we'll I suppose see later that it's important where the water flows. These are still rib-like kind of things. And the time scale here that's 700 years. To be taken with a certain grain of salt, because it does depend on what this delta is, and the delta was the wrong value of delta. So here's another one where he's just changed, I think he's just changed beta. I'm just going to run through a bunch of these things just to see what happens. Also, I should say that what you get coming out is, or what you see at the end, depends on how long you run this thing for. When he's running these things, it takes a day to run one of these things. So if you're writing a thesis and you're experimenting with this, there is a competition between how long you can spend doing it, and you've got to write a thesis. So, but this is sort of Drumlin-like in my kind of view. You have blue low stuff, brown high stuff. But actually, if you look closely in here, down to the bottom right, you can see there's numerical instability going on here. There's rapid fluctuations at the grid scale. So things are running into numerical problems. Here's the same, I think, but then now it's the water flow. And I think what's probably going to happen here is that you'll find that the water kind of mostly goes around the drumlins, which is kind of what you expect, because the 3-dimensionality is associated with this rilling instability, which is associated with water flow. So where there's more water flow is going to be where you're excavating the sediment more, and therefore lowering the flow. And you can sort of see that there, I think. Now what he's done is delta has gone up to 0.5, which is getting further away from where you want to be. And I think the time scale here will go much faster, but that's associated with this change in delta. So you start out with ribs, and then they become kind of drumlinized like that. And then I think at the end of this, I think we're going to have an optical illusion. So now they start aligning, and then there's the optical illusion. But what you're seeing is you're seeing a lot of things which I would interpret as megascale glacial lineations forming, except that they're not parallel to the ice flow, which is left to right. They're skewed, and I'll say something about that in a minute. I think this is the same picture, but now you have the water flow, or the hydraulic potential lines, and eventually what happens as you start forming these lineations is that the water starts to become concentrated in the deep bits, in the troughs between the high bits, which are brown. I don't think he goes all the way to the end of this, but he goes sufficiently far that you can sort of see that the water flow, largely speaking, is concentrating in the troughs. Here is one, so near the end of the movies. Now this one, I can't actually remember when he did this. It must have been after his doctorate, because delta is 0.005 in here. So now you're kind of getting down to where you want to be. I have a feeling this took a week to run or something like that. But again, what you get is the amplitude still in the order of meters. It's not really as high as you'd want. The drumlins, which are pretty drumlin-like, are all moving downstream, and that's a feature of all of these results. And then you end up with, that looks pretty passable interpretation of the sort of topography. I think the next one is, this is actually the depth of the water film, and this ends up looking like a lot of fish swimming upstream to me. So the red bits are where the water is concentrated. So they're like little pools of water which will be located in the downstream of the drumlins. So this is just a snapshot to indicate, so we're back up to delta's 0.1. This is the sort of rib type version. And here is the same picture now with a snapshot of the hydraulic flow lines, which are wandering, and they're concentrated in streams, but not particularly, well, there's no sort of channels going through the thing. Here is the drumlin-like thing at the end. Here is looking at it from the side, which has two aspects to this. First of all, this looks to me like nice drumlinized topography, but also what you can see is you see these things which were visible before, but these spikes down here indicating numerical instability. I want to go the other way. So there are the inclined MSGL-like features growing. You want them to be parallel to the ice flow, but they're transverse. And here is the associated water flow, which is mostly going up along the ridges. Now, the reason in the numerical solution that we're getting these MSGL, but they're inclined, is because they're associated with water flow, and because you have periodic boundary conditions, there is nothing to prevent in the numerical solution water flux, there being a non-zero water flux across the domain from bottom to top. And that's what's happening here. But in reality, because it's an elliptical problem, even if it's a little kind of square in the middle of an ice sheet or an ice stream, in reality, because it's elliptical and because you should have no flux, lateral flux at the edges, you should have no flux top and bottom boundary conditions. So in order to improve this model, you need to prevent lateral water flux, which means you need to change the boundary conditions, and that hasn't been done. And I believe that will then make these MSGL parallel to ice flow, which is what you want. So there are issues with this theory, and I'm kind of running out of time, which is good because I'm running out of talk. And I've put some of them up here. And the first one is about this water film constitutive relation between the water film depth and the effective pressure. And we're just making something up. And so you'd like that to come out of some proper theoretical description. The kind of ingredient you want to say is that actually, if you have a saturated granular material, you know that there is a relation. It's just, it's basically normal consolidation theory for saturated soils. There's a relation between the porosity of the medium and the effective pressure. So basically, if you take a saturated soil and you stand on it, it's squeezed, it changes the porosity. So when you go to a beach and it's water saturated, you stand on it, you see there's water flow because the porosity changes. So in general, you would want to say there's a relation between effective pressure and porosity. And the way I would like to think about this funny closure or constitutive relation is that really the water film is really sort of like a boundary layer on the top of this compressible porous medium. So that might be one way to get into this, but I don't know. I talked about sediment transport, but if you actually work out the numbers, and in here you see, with sediment transport, you're talking about a water film that is millimeters thick. So that's not going to transport anything. So in this theory, but you have the same problem if you're trying to build river systems or rills or rivulets on hill slope, because if you rain, meter a year, whatever it is out there, on a hill slope, and you write down a theory, you'll get a millimeter thick water film, and that doesn't erode anything. But in reality, what happens in a hill slope is you have storms, whoosh, that takes the stuff off. You model it in the same way as an average, but actually the damage is done by storms. Here, the equivalent of the storm has to be the subglacial flood, and that sounds a bit idealistic, except that subglacial floods under Antarctica have been observed in a variety of ways, actually directly, but also through up and down motion of the ice sheet. So another drawback of this theory is that the drumlins all move, but you want them to be stationary. And the reason you want them to be stationary is because of this problem of some drumlins have internal stratification, so that they say they will contain lenses of sand and gravel, which is water derived. And how can that be if they're all moving? And the answer, so the idea would be, let's stop the drumlins moving, but how do you do that? In this theory, they're always moving because the ice is always dragging the till. What I've called slipping and shearing here involves the idea, which has been observed in the laboratory, that when ice slides over till, part of the motion is due to shearing of the till beneath, but part is due to actual slipping between the ice and the till surface. So the ice has to go at essentially a constant rate here, but how much is due to slipping and how much is due to shearing is, it's not included in the present version of this theory. And I have a feeling that there is a mechanism that if you accommodate all of the sliding by slipping, then because the till becomes stiff as it gains in elevation, then you'll stop these things moving. And then there's the whole issue of numerical approximation, how you solve this, which is... So I'm going to stop there and leave you with philosophical things to ponder.
Your equations are scale invariant, right? Because you have them in dimensional form.
So, so there's several answers to this. So there are lots of subglacial topography, types of subglacial topography, which forms what everybody's heard of terminal moraines. Well, you know, basically the front, the ice acts as a bulldozer and pushes stuff forward in front of it and then retreats and leaves it behind. You have came terrace, you have kettle holes, which are left all when the ice retreats. There's an example of a glacier, Mulajökull in Iceland, which is a Piedmont glacier, which sort of flows out like that. And it goes backwards and forwards, and it has actually formed drumlins, which and people have been out to observe these things and measure them and so on. So there's a process there where proper drumlins are being formed at the front of a glacier as it goes backwards and forwards. And then the other thing I was going to say, which is that there are other things called glacial flutes, which are sort of like lineations, but the scale is hundreds of meters long and meters wide, and they are commonly associated with a boulder and placed in the till, and then the ice flows over it, and then in some mechanism which people don't really properly understand, they form, but they're unrelated to these kind of things. So, but there are a number of different features of this type. I'm not sure if that's answering your question, actually. But.
Well, I guess part of what I'm hearing is that if you go to the smaller scale, there would be, I guess, the theory doesn't include not necessarily all the effects.
Yeah, so people have measured, geographers do what geographers do, which is they map everything. And so there are, for example, there's in Britain, there is they've mapped something like 37,000 drumlins. And then, you somehow, because of course they're funny shapes, but you decide what the length is and what the width is and what the elevation is, and then you statistically, say what, and what you find is that there's no drumlin that in this mapping exercise that's shorter than, I think it's about 100 meters. So there seems to be, there's a cutoff down there. And actually, I think, top of my head, when you look at this stability diagram, you see down at the, no, I'm thinking the wrong way around. I was thinking of small wave number, but I actually should be thinking of large wave number. But actually, I didn't mention that. When you look at the stability diagram, so, I write down these equations. I have no idea what kind of equations they are. You sort of hope everything's well posed. When you look at stability, and then what you see is the growth rate. Now, it actually decays as the wave number goes off to infinity. So it's not completely ill-posed, and it's not going off to constant. It decays to zero. What you'd want is that you'd want it to go down to a minus infinity. You'd want some diffusive type thing in there to kill off high wave numbers, and that's not in this. And I don't know whether there is something missing that would do that.
Okay. I have a question, Andrew. The movie seems to show that obviously nonlinearity is important because you can see these features merge and deform, and finally it gives you a preferred scale. But is the end result predictable by linear theory?
No.
No, it's not. So it's completely nonlinear.
Linear theory is just kind of, you do it because you can do it, and because you're, you would say the same about any of these kind of things. Well, railways is a good example where there's perfectly good linear theory. It's unstable. If the Froude number is bigger than 2, what you end up with is those things which are periodic shock waves, so they don't look remotely sinusoidal. And basically that's the story with anything. Linear gets you underway. It's a sort of, it's an ingredient for the process to get started, but what you end up with is miles away from it.
It gives you the wrong answer.
It gives you, the fact that the instability gives you the right wavelengths is kind of heartening. Actually, but it's not quite like that. And in fact, going back to your question, where the length scales are good is you scale the model. You're doing the whole balance terms, It's the scaling that gives you the wavelength, right? when you look at the instability, I mean, then it's less easy to see exactly what's happening. But in the stability maps I showed, you're basically getting instability occurring order 1 wave numbers, which is, sort of right ballpark. But as I said, the growth rate is not, it's not very focused. The growth rate is still positive when you've got large wave numbers and so on. And I think probably actually in the earlier movies, what you saw is the initial instability, very short-lived. Initial instability is a very short wavelength, and then they very rapidly coarsen. And that's probably coming out of the fact that you're putting in, Gaussian, some kind of white noise, which has got high wave numbers in it, which are unstable, but then they rapidly merge and they coarsen.
Very good. If there are no further questions, there's one.
So about the numerical instability, aside from making the maps appear a bit untidy, what in your mind are sort of the impacts of these numerical instabilities?
Yeah, I mean, I mean, the last time we met, so we had a conference. I mean, this was a little bit of it, but the four principal people, James Fan and Ian Moyles, who were the latter movies, and then Mike Chapoigne, who was the earlier movies, and we were all at the same meeting, and then we were conversing about, can we kind of move this on? So one of the problems you have in this is you've got B, the elevation of the till, you've got S, the elevation of the ice surface, and H, which is the difference between them. But of course you have a water flow equation, so there's a hidden dH by dt in there. It disappears because it's very small. But in principle, you've got 3 evolution equations for 3 variables with a geometric relation between them. So, I mean, what's that doing? But when you implement this, so the dH by dt has disappeared, so, and then what you do is you say, we'll step forward B in time, we step forward S in time, seems like a reasonable thing to do. We'll then compute H, the film thickness, is going to be S minus B divided by delta. Delta you want to be very small, so you can imagine this is kind of just, you've got to, when you coding this, you've got to step your way through it and do things in a certain order. What you might do is you might change the order. You might say, oh, well, delta is small, so why don't we just say B is approximately S, and then we step forward B and then use the S equation to do, not step S, but actually to define what the phi is or something. You might do that. The potential problem you have with that is that you can think by analogy with what you do in hill slope evolution, where you have the same problem, which is you have a water film moving over erodible substrate, don't have any ice, and you have the same delta in that problem, and then you might say, let's put delta to 0 because it's very small, who cares? And then that problem becomes ill-posed, and really ill-posed because you get k-squared growth rate at infinity. So, and that's associated with the asymptotic limit when delta is small regularizes it. So, there's in dealing with this numerically, I mean, what we never had in here was, basically a professional numerical analyst who's, let's march in here. But I can also see why people would not want to do that, because you don't really know what the kind of beast you're dealing with is, which makes it fun, of course.
Okay, we have a reception